All right, so it's been a while, but we're going to pick back up talking about Coulomb's law. Really, what Coulomb's law allows us to do is when we start talking about, what do opposite charges do to each other, what do like charges do to each other, typically the answers are, opposite charges attract, like charges repel each other. But really, what we're looking at is like charges push away from each other, opposite charges pull towards each other. So we have a push or a pull. Way back towards the beginning of class, we learned that pushes and pulls were actually forces. So Coulomb's law allows us to actually find essentially the electric force. Get Flipboard out of there. All right, so they allow us to find the electric force. And really what Coulomb found is that the electric force is equal to a constant, in this case we're going to call it Coulomb's constant, times, I like to put it in parentheses here, the charge of the first object times the charge on the second object divided by the distance or radius between them squared. Okay, so just like we did with gravity, we kind of have this r being squared, the distance between them squared, meaning the farther apart they are, we see that it decreases exponentially. All right, so typically r and the charges, distance and the charges are either going to be given to us or that's what we're going to be looking for. So then it just leaves a matter of, well, what's this constant? What is Kc? And the Kc that we're going to use time and time and time again is going to be 8.99 times 10. I got to get a desk. I got to figure out what this is. Give me 1 second. Looking. Times 10 to the 9th is what it looks like. All right. So 8.99 times 10 to the 9th. And then even looking here, if I wanted to know what my unit is here, I know that I'm going to end up with charge or coulombs squared on top since I've got coulombs times coulombs. I got meters squared on the bottom here. So figuring out that is essentially, I can kind of just do the opposite is, so I've got meters squared over coulomb squared. The other thing though is if this is helping me find force, so I know force is in newtons. So in order for all that math to make sense, it's going to be Newton meter squared per Coulomb squared. Okay, so that's the unit for Kc. And that's the only constant for Kc I'm ever going to have you use because the distance we're only ever going to use is meters. Charge is only ever going to be in coulombs and force is always in newtons because yay, metric system. All right. So let's actually use Coulomb's law and let's figure out what is the force of attraction, the electric force of attraction between a proton and electron, specifically in a hydrogen atom. All right, so I know Kc, and essentially I'm just going to kind of box that because this is the stuff that you're going to want to have written down. This is the important stuff, all right? And then I'm going to go into my practice problem. So we're going to say my practice problem is involving a proton and an electron in a hydrogen atom. And why hydrogen? Go into a little bit of chemistry here. Really, 99.997% roundabouts percent of all hydrogen atoms are pretty much just a proton with an electron in orbit around it. But we know, their opposite charges repel or opposite charges attract. So let's actually figure out what's the force of attraction here, right? So I'm looking for the electric force. I'm just going to abbreviate that elect there, okay? So we need to know a couple things. We need to know, not the mass of the proton, we need to know the charge of the proton, and I'm even going to say we'll do QP, that'll be my one. The charge of a proton typically we would say that it's, +1 if we're just talking about chemistry, and electrons are -1. But that doesn't really help us out trying to use Coulomb's law because we need it in coulombs. And really, the charge of a proton is, I'm going to put positive, 1.6 times 10 to the negative 19th. Okay, it takes a lot of protons to actually get up to 1 Coulomb, and then that'll be capital C. So now I need the charge of an electron. Well, if a proton was positive 1, and now it's positive 1.6 times 10 to the negative 19th, an electron's just going to be the opposite of that. It's just going to be negative 1.6 times 10 to the negative 19th coulombs. Okay, the positive and negative part still important, just because it's going to help us know if these things are being pushed away from each other, if they're being pulled towards each other, stuff like that. All right, and figure out R to figure out just how far apart these things are. Essentially, a little bit of Google searching will tell you that these things are 5.3 times 10 raised to the negative 9th meter. All right, so super, 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 super small. And keep in mind, that's just a number I grabbed online. It might be completely wrong. Right now, though, I have everything I need in order to solve for the electric force there. So let's even just start typing things in. Okay, so we've got the electric force is equal to Kc, which we said was, and I like parentheses, 8.99 times 10 to the 9th newtons meter squared per coulomb squared. And this is going to be multiplied by, I'm actually going to make that a bracket. Charge 1, which we're saying is the charge of a proton. So we've got, hold on, try to get that out of the way. Okay. Positive 1.6 times 10 to the negative 19th coulombs times charge 2, which I'm saying the electron's charge to negative 1.6 times 10 to the negative 19 coulombs, all over the distance between them, r squared, so 5.3 times 10 to the negative 9th. But I'm squaring that, close my brackets. All right, so now I just need to be able to type all of this in. Let's see how well my calculator works for that. All right, so I've got parentheses 8.99 times 10 raised to the 9th power, closing parentheses, times open parentheses, 1.6 times 10 raised to the 19 negative, close that parentheses, times open parentheses, 1.6, oh, got to make that negative, times 10 raised to the negative 19th power, closing parentheses, divided by open parentheses, 5.3 times 10 raised to the negative 9th power, closing parentheses, square that, close parentheses, equals this really, 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 really small number. All right, so I'm just going to go with negative 8.2 times 10 raised to the negative 12th power. All right, out of here, Flipboard. Times 10 to the negative 12th. And once again, doing some unit kind of analysis here. All right, so I've got meters there. So I've got meters times meters, so that's meter squared. That's going to cancel that. Meter squared. Coulombs times coulombs, that's coulomb squared. Cancel this coulomb squared. I'm left with newtons. I'm looking for force, so that makes complete sense. All right, so just looking at the kind of electric force here, the electric attraction between the proton and the electron. We're looking at negative 8.2 times 10 to the negative 12th newtons. Essentially, that's how you use Coulomb's law. Keep in mind, for the most part, you're not using charges that are super, super, super small like that. You're not using distances that are super small as well. Typically, you're using masses, charges and distances that are kind of at R scale. So millimeters to meters, uh, fractions of a coulomb, to multiple coulombs for charge. You're not doing things like times 10 to the negative 19th. You're going to do things way easier. I think that where this gets really interesting, though, is when we start comparing the electrical attraction between the proton and the electron to the gravitational one. So we know that there's, a force of gravity. Let's even go back. I'm gonna make that big G, not little g, mass times acceleration due to gravity. This one was equal to Avogadro's number, m1, m2 over r squared. And so looking at this one then, the gravitational constant is 6.67 times 10 to the negative 11th. And we're looking at meters cubed over kilogram second squared. All right, so that's the gravitational constant, the universal gravitational constant, or Newton's constant. Really though, so let's go ahead and take that, throw that in parentheses. I'm going to take that times the mass of a proton. Here, these numbers are not going to be the same. I've got 1.67 times 10 to the negative 27th kilogram times the mass of an electron, which is 9. And this is using, I think, some pretty modern data here. Times 10 to the negative 31 kilograms. That's with 3. All right. The distance between them, though, is going to be the same. 5.3 times 10 to the negative 9th. But that's squared, and that's meters. Keep in mind with this gravitational constant, like they separated kilograms into like kilogram, meters per second squared is essentially to get me 2 newtons there at the end. In any case, I might have that unit wrong anyway, but the math is going to work out the same way. So now when I go in to calculate this out, so I've got 6.67 times 10 raised to the negative 11th times open 1.67 times 10 raised to the negative 27th power, closing parentheses, times open parentheses 9.1 times 10 raised to the negative 31st power, close parentheses, divided by open parentheses 5.3 times 10 raised to the negative 9th power. That's squared. Closing parentheses equals 3.6 times 10 to the negative 51. 3.6 times 10 to the negative 51. Once again, though, we're still looking for force, so that'll be in newtons. All right. I think, though, this is where where we get to start comparing two forces. Like, there's an attractive force between the proton and electron, really, really, really small, okay? But since protons and electrons both have mass, they should also have this force of gravity pulling them together as well. And when you go ahead and calculate that out, it's super small. I mean, just looking at the exponents on the 10 there. With the electric force, we're looking at negative 12. On the gravitational force, it's negative 51. So this is super small. And this is why we see the gravitational force really only has an effect when the masses get to be way bigger than what we're working with here. All right, so big thing though with this one, with this video and stuff, was to go through Coulomb's law. Really, it's just your Coulomb's constant times the two charges divided by the distance between them squared. One thing I do want to point out though, forces that are a negative number, like what we have here, essentially that's an attractive force between them. So if we had a positive charge and a negative charge, we'd end up with a negative number, and that's an attractive force. If they were both protons, in which case the only thing we'd be changing here is just the sign here. That'd be a positive number because it'd be the same value, just change the sign here. We got positive times a positive. We'd get a positive force, and that means it's a repulsive force. They're pushing away from each other. Same thing if we were working with two different electrons, is we'd have a negative here and a negative here. This would just be a negative. Negative times a negative is a positive, so we still have these electrons positively repelling each other. Pretty basic. But yeah, so that's Coulomb's law. Uh, there are some practice problems stuff, so good luck with that. Otherwise, we are going to start, we're going to look at electric fields tomorrow, which is essentially just kind of one way to think of it is just a force exerted by a single charge. All right. But with that, good luck with Coulomb's law.